is the universe? For almost a century, we've had a confident answer: 13.8 billion years. It is difficult to imagine that just over 90 years ago, we did not know about the existence of most of the universe around us. These great islands universes we call galaxies. We built a grand story of cosmic creation, one that begins with the Big Bang and unfolds slowly, gradually over those 13.8 billion years. But what if that story, our standard model of cosmology, has a few pages wrong? In fact, what if the first chapter needs a complete rewrite? Humanity's newest eye on the cosmos, the James Webb Space Telescope, is now sending back data that challenges our most fundamental timelines. The images are beautiful, but the message they carry is a remarkable one. It's forcing us to ask questions we thought were long settled. For decades, our understanding of everything has been built on a single, powerful idea, the lambda cold dark matter model, or lambda CDM. This is the standard model of cosmology, and its success has been astonishing. It paints a picture that starts 13.8 billion years ago with the Big Bang, an event of unimaginable density and heat. From that moment, the universe has been expanding and cooling. The classic analogy is a loaf of raisin bread rising in an oven. The dough is space-time, and it's always expanding. The raisins are the galaxies, and they aren't moving through the dough, but are being carried apart by it. The further the raisin, the faster it seems to move away. This is our expanding universe. Within this model, scientists laid out a clear timeline for how things should form. After a hot, dense plasma phase came the cosmic dark ages, a universe filled with a fog of neutral hydrogen gas, but no stars or galaxies. Then, gravity would slowly work its magic on tiny density fluctuations left over from the Big Bang. The prediction was clear. The first stars would ignite, followed by the first small, clumpy, and primitive galaxies, what astronomers called proto-galaxies. Over billions of years, these infant galaxies would collide and merge, building themselves up into the grand spirals we see today, like our own Milky Way. This story was supported by decades of evidence, from the Hubble telescope to the faint afterglow of the Big Bang itself. All we needed was a telescope powerful enough to peer back into that cosmic dawn and find those faint baby galaxies, confirming the story we were so sure was true. Cut to the James Webb Space Telescope. A true technological marvel, its massive golden mirror was designed to capture the faint red-shifted light from the edge of the observable universe. It is a time machine, built to see the cosmos as it was more than 13.5 billion years ago. Its mission was to find the evidence that would cement the standard model. But when the first images came back, there was a problem. The telescope worked perfectly. The issue wasn't the instrument, it was what it saw. Instead of the faint, wispy proto-galaxies everyone expected, Webb found a sprawling, brightly lit metropolis in the primordial darkness, a new cosmic conundrum. Since it began its work, JWST has revealed far more ancient, luminous galaxies than our theories ever allowed for, creating a powerful tension with our established models. For here's a shocking discovery. Astronomers are now finding galaxy candidates at redshifts that push us closer and closer to the Big Bang itself. The current record holder, a galaxy called JADE's GSZ 14-0, is seen as it was just under 300 million years after the Big Bang. Other candidates might be even older, existing just 200 million years after the universe began. But it's not just their age, it's their maturity. Some of these ancient galaxies show signs of complex elements like oxygen, which should have taken hundreds of millions of years of stellar evolution to create. This suggests multiple generations of stars had already lived and died, a process that was supposed to take much, much longer. The model simply can't explain how dark matter could have gathered enough mass so quickly to host such large and bright galaxies. The trouble didn't begin with Webb. For years, cosmology has faced a problem known as the Hubble tension. To basically sum it up, we have two main ways of measuring the universe's expansion rate: and they give us two different numbers. One method looks at the local universe nearby, and the other looks at the early universe through the cosmic microwave background. The numbers don't match. This suggested something might be missing from our standard model. Now, Webb's findings have thrown fuel on that fire. The discovery of these impossibly early galaxies introduces a new parallel line of tension. Our standard model is now being squeezed from two sides. Its predictions about the expansion rate don't match local measurements, and its predictions about galaxy formation don't match what Webb is seeing in the past. This has sent theorists scrambling. Perhaps the CDM, or cold dark matter part of the model, is wrong. Maybe dark matter isn't so cold and interacts in ways that let gravity build things faster. Or perhaps the physics of the first stars needs a radical rethink. Maybe they were far more massive and brighter than we assumed. Some researchers even suggest we're not seeing more stars, but rather extreme brightness caused by gas falling into supermassive black holes much earlier than expected. These are not small tweaks, they are fundamental revisions to our cosmic story. While opening up new cosmic conundra, Webb is also solving old ones. A huge question has always been the epoch of reionization, the moment the universe-wide fog of the cosmic dark ages was cleared, making the cosmos transparent. What produced the flood of radiation that did this? Webb has provided a compelling answer. It appears the heavy lifting was done by countless tiny, low-mass galaxies. Individually small, they were incredibly numerous and furiously forming stars in starbursts. Together, they produced enough ultraviolet light to ionize the universe and bring about the cosmic dawn. But as Webb clarifies one issue, its data gives life to more speculative ideas. In a random universe, you'd expect a 50-50 split of galaxies spinning clockwise versus counterclockwise. Yet one controversial study of Webb's images reported an imbalance, hinting that the universe itself might have been born spinning. This aligns with a fringe theory called black hole cosmology, which posits our universe could be the interior of a giant spinning black hole. This is highly speculative, but it shows just how profoundly Webb is shaking up the field. So, has the James Webb Space Telescope proven the Big Bang wrong? No. But it has revealed that the standard model that grew from it, Lambda CDM, is incomplete. The smooth, orderly timeline we once held dear is being replaced by a more chaotic, dynamic, and rapid story. We went looking for the faint embers of cosmic dawn, and in fact, we found a raging fire. The universe was building complex structures far earlier and faster than we ever thought possible. The era of settled cosmology is over. The Webb telescope hasn't given us neat confirmations, it's given us a profound gift, a set of deep, new mysteries. What do you guys have to say? Are these findings just a puzzle to be solved within our current theories, or do we need a new approach entirely? Let us know in the comments below.